This is the course Mechanical Vibrations. My name is Carmen Muller-Karger. Today we will study the harmonically excited viscous damped systems. This is part of the chapter 3 of our textbook round and represents a continuation of our previous presentation, which was harmonically excited undamped systems. We will study 3 different cases. The first one will be a mass spring damped system subjected to a harmonic force. We will find the absolute response and we will find the force transmitted to the base, which, as you see, will be the force transmitted by the damper and the force transmitted by the spring. The second case will be when we have a moving base, and we will find the absolute response of the mass and the relative response of the mass. We will call it C, and will be the absolute minus the displacement of the base. And then we will find also the force transmitted to the base. The last case will be the rotating unbalance, in which case the vibrating force becomes ME, which is the unbalance, times the rotating frequency of the system times a sinusoidal function. We will find the absolute response and the force transmitted to the base. Let's start with the first case, harmonic force. We have a mass dampered spring system, and this is the equation of motion, and it is subjected to a harmonic force, in this case, for example, a cosine of omega t with an amplitude of f0. We will have a particular solution and an homogeneous solution to complete the total solution. The particular solution will be of the same form of the excitation force, and it will be cosine of omega t and the derivative of that force, sine of omega t. So, and we have to find the constants A and B. To find the constants, we will derive the particular solution, find the velocity, which will be multiplied by the damper coefficient, and then the second derivative, which will be the acceleration, will be multiplied by the mass. Remember that the homogeneous solution, we did study that when we study free vibrations, and very important that constant C1 and C2 are a function of the initial condition, but we cannot take the constant what we already found. We have to find the constant for the whole solution. So first we will find the particular solutions, finding A and B, and then we will find the constants C1 and C2. Coming back to finding the constants A and B, we'll introduce these 3 equations into our equation of motion, and then we have mass times the acceleration, which is this one right here, the constant of the damper times the velocity, and the constant of the spring times the displacement, which is the first equation right here. And all that will be equals to my external force, which is F0 cosine of omega t. I will group the terms that multiply the cosine, and I will group the terms that multiply the sine. And as you see, the ones that multiply the cosine will be equals to F0, and the ones that multiply the sine will be equals to 0. Then I have 2 equations with the 2 unknowns A and B, and then with a little bit of algebra, I find the values for A and I find the value for B. If I put those equations in terms of my natural frequency, which is square root of K over M, my zeta, which is the damping ratio, which is the damper coefficient divided by the critical damping, and the frequency ratio, which is the frequency of the external force divided by my natural frequency, A and B will become this expression and this expression. So we just found A and B, which are the constants of the particular solution and are a sum of harmonic functions. any sum of harmonic functions can be also expressed as a single harmonic function. Let's say we choose to be a cosine. So if the function is a cosine, the excitation, I like to express it in a cosine as well. And we can demonstrate, as we did actually in the first chapter when we study harmonic motions, we can find that the amplitude of this only one harmonic motion will be the square root of a squared plus b squared. And this phase angle will be the inverse tangent of b over a. If we have a sinusoidal function as my excitation force, I would like to express the response in terms of a sine function. And the values for the amplitude and the phase angle will be exactly the same. You can do the exercise of, if you have a cosine function as the excitation, can find it as a sine, but then the phase angle will be just displayed 90 degrees. We go back to our particular solution that we can express as a sum of two harmonic functions or a single harmonic function with a phase angle. And we know that the values for a and b are these two. So if we want to find amplitude of the particular solution, will be the square root of a squared plus the b squared. And that gives me this value over here. And the inverse tangent of b over a, the denominator cancel out, and I get this expression right here. Therefore, we were able to find the response of my systems in terms of the characteristics of the system, which are the constant of the spring, the mass, and the damper constant. And with this is the phase angle, and this will be the quotient between the amplitude of the response respect to the magnitude of the excitation force. We can also express our solution not in terms of the characteristics K, C, and M, but in terms of the natural frequency of the system, which you remember is the square root of the constant of the spring divided by the mass, zeta, which is the damping ratio, which relates C, K, and M, and the frequency ratio. We found that A and B, which are these two constants, can be expressed with these equations. And now if I take the square root of a squared plus b squared, I get this value over here. And this is the phase angle. Now we can express our solution as f sub 0 over k, also the static deflection, and we can call this term over here, which this is this over here, which is in this orange box, the magnification factor. And our response will be the static deflection, which is the magnitude of the force divided by the constant of the spring, times the magnification factor times the cosinusoidal function, which is in terms of the same frequency as the excitation force minus the phase angle. Let's now analyze the graph of the magnification factor. Remember that this is the expression for the magnification factor, and it is the maximum amplitude divided by the static deflection produced by the magnitude of the force. As you see, if zeta is equals to 0, these terms become 0, and this expression is exactly the same as the one that we analyzed for undamped system. Any amount of damping, zeta greater than 0, reduces the magnification factor for all values of frequency. As you see, every single curve for zeta 0.1, 0.2, 0.3, 0.4 are less than the green one, which is zeta equals to 0. For frequencies that are equals to 0, it means that the force will be only a constant force. The magnification factor becomes 1. Particularly when R is equals to 1, the reduction of the magnification factor is very significant in the presence of damping. For very, very high values of frequency where R goes to infinity, the magnification factor goes equals to 0. That's the example that we said, that when we have very high frequency excitation, the system doesn't produce a response in the system. The maximum value of the magnification factor is not exactly at R equals 1. If we want to find this maximum that is a little bit shifted to the left, we will have to derive this course. Let's do that. So the maximum takes place in the derivative of that expression respect to R, and if we derive this expression and find R, we find that the R critical, or the R where we have the maximum magnification factor, is in square root of 1 minus 2 zeta squared. So this is what we call the critical frequency of excitation. And the value for the magnification factor at that R is equals to this expression right here, which is 1 over 2 zeta square root of 1 minus zeta squared. At R1, the magnification factor takes the value of 1 over 2 zeta. And as you see, for values of zeta greater than 0.7, we do not have a maximum anymore. The curve for the amplification factor becomes flat. In these slides, we have the characteristics that we just observed in our graph, where we said that for damping equals to 0, when R is 1, we call that phenomenon resonance, and the magnification factor becomes infinity. Any amount of damping reduces the magnification factor for all force in frequency. For R equals 0, M is equals to 1 for any damping of the system. The reduction of M is very significant in the presence of damping near resonance. The amplitude of force vibration becomes very small for very high frequencies. So when R goes to infinity, M goes to 0. The maximum value of M does not occur exactly at resonance when we have damping, and this is the critical value that we calculated by deriving the expression of M, and the maximum value can be calculated with this expression. For R equals 1, M is equals to 1 over 2 zeta, and remember that for zeta values greater than 0.7, M decreases monotonically. Now let's look at the phase angle. This is the expression for the phase angle, and as you see, if this is the excitation and this is the response, the amplitude could be different, the frequency is the same, but the response leads to the excitation by a phase angle. For R less than 1, which are here, the angles are always less than 90. For R equals to 1, the phase angle is always 90 degrees, regardless the value of the damping ratio. And for R greater than 1, all the phase angles are always greater than 90 degrees. Now let's study the force transmitted to the base by a viscous damp system. If we have, for example, this platform where we have two machines, this machine is being excited by a force F sub 0 cosine of omega t. This force produces a response of this machine. And then if we do a free body diagram of the platform right here, we see that this response produces a force which is equals to K times this X and C times X dot. This is the equation for that force that this platform is receiving. We can imagine that this force will travel along the platform and eventually will hit another element, another machine, and that other system could be excited so that it produces a response of the same frequency as the one that it was excited the other machine. So that's why it's very important to study the forces transmitted to the base. Let's find the expression for the force transmitted to the base or foundation of this viscous damp system. This is a steady-state response in terms of the mass, the constant of the spring, and the constant of the damper, and the frequency of the excitation force. And this response is for a excitation which has constant amplitude, and the frequency of excitation is omega. We draw the free body diagram of the base, and we have the force of the spring and the force of the damper. The force of the spring will be K times this expression right here, where I call this the amplitude of the response, and the velocity will be the derivative of this expression will be, this is a constant if we consider that the frequency is constant, and the derivative of cosine is negative sine, and then the internal derivative of the sine is omega. We can always convert a summation of a cosine and sine in a single cosine function with a phase angle. We already have a phase angle here, which represents the phase angle of this response respect to the excitation force. Now we have a other phase angle, which is the phase angle between this force transmitted to the foundation and the response of the system. The phase angle alpha has this form over here, and if we introduce the value for the amplitude of the response, which is f sub 0, 1 over square root of k minus m omega square, all that square, plus c omega, all that square, which is these terms over here, we have this expression for the force transmitted to the base. We can also find this same force transmitted to the base, but now in terms of omega n, theta, and the frequency ratio, which will give me that the response is the static deflection times the magnification factor. And remember, this is the expression for the magnification factor. And then if we introduce this same expression that we have for the previous slides, we get this expression right here, and we also can get this square root in terms of theta, omega n, and r, and then we get that the force transmitted to the base can be in terms of this factor right here. This factor is what we are going to call the transmissibility coefficient. And again, we have two phase angles, and we can actually call this addition of these two phase angles one phase angle, and it will be the angle between the applied force and the force transmitted to the base. The same way that we graph the amplification factor, we can graph the transmissibility factor. And this will be this graph right here. We can pull out some characteristics of this graph. For example, that R equals 0, it means no frequency. It means a constant force. The transmitted force will be equals to the magnitude of the force. For undamped systems, theta equals to 0. At resonance, these transmissibility factors tends to infinity. It means that if we are in resonance, the force transmitted to the base is very, very large. For values of R greatest than square root of 2, all the values of the transmissibility factors are less than 1. And for the value R equals square root of 2, the transmissibility factor is equals to 1, independent of the amount of damping of the system. For values less than square root of 2, the less amount of damping, the greater the transmissibility factor, but after square root of 2, the transmissibility factor is greater for bigger amount of damping. In this slide here, we summarize the characteristics we talked about using the graph of the transmissibility factor. The last one transmissibility factor attains a maximum for zeta greater than 0 and less than 1 for frequency ratio equals to this expression right here. This term over here is a little bit less than 1. We finished studying the case when we apply a harmonic force to a mass damper spring system. We analyzed the absolute response and the force transmitted to the base. Let's move on to the second case when we have a harmonic displacement of the base. We will find the absolute response, the relative response, and the force transmitted to the base. Examples of this kind of excitation would be the landing gear of an airplane. Here we have the mass of the aircraft. Then we have the suspension, which will be modeled as a spring and a damper. And then we have that the wheel is subjected to a displacement. It could be modeled as a harmonic force. Another case will be the vibration measuring equipment. At the end of this chapter, we will study the vibrations pickup. We will study device that measure displacement and device that measure acceleration. To get the equation of motion, let's do our free body diagram. We have our mass, the force of the spring, and the force of the damper. The force of the spring is equal to the constant of the spring times the relative displacement between the two ends of the spring. In one end, I have the absolute motion of the mass measured from the equilibrium position, and in the other end, I have the displacement of the base. And the force of the spring will be equals to k times x minus y. The force of the damper will be the constant of the damper and the relative velocity of the two ends of the damper, which is c times x dot minus y dot. Adding forces in my vertical direction, I have the force of the damper plus the force of the spring equals to the inertia forces, which is mass times acceleration. If the mass goes downwards, I have a negative sign. We have the displacement of the base is y, and we derive this expression to get the velocity of the base, and that will be y sub 0, the derivative of sine, which is cosine, times the internal derivative, which is omega. Then we have that we can write all the terms that involve x in one side of the equation and the ones that are with y in the other side of the equation. And there we get m two dots plus c dot plus k is equals to the c times the velocity of the base plus k times the displacement of the base. The sum of two harmonic forces, I can write it as a single cosine with a phase angle, and this will be the phase angle. This over here will be my excitation force. Now that we have the equation of motion and we have an excitation force, and the force looks very similar to the previous case where we have an amplitude of the force, we can write the particular response. Let's do it first in terms of the mass, the constant of the springs, and the constant of the damper. And then we have F sub 0, which is all this term over here, times this term, which involves the characteristics of the system. And if we substitute F sub 0 by this amplitude, we get this expression, and we can write it as y sub 0, which is the amplitude of the displacement of the base, times this coefficient cosine of omega t minus a phase angle. And the phase angle is the addition of alpha plus phi, and those are the two phase angles. We can also write the response in terms of omega n, the damping coefficient, and the frequency ratio. If we divide this term by k, then we got that this is F sub 0, and we can substitute c over k times omega by 2 zeta r squared. And you recall that when we had this type of excitation, our response was the static deflation times the magnification factor. And this is the magnification factor. We can also write the phase angles in terms of omega n, zeta, and r with these expressions. And if I substitute the value for the magnification factor and for f sub 0, which is this term over here, we get this expression right here. And we have already studied this coefficient. And when we add those two angles, we get this expression in terms of the damping ratio and the frequency ratio. In conclusion, when we have this type of external force, which is caused by a moving base, we have this response. And the ratio between the amplitude of the response and the amplitude of the base motion is called the displacement transmissibility. And as you see, it has the same form as the transmissibility factor we studied for the force transmitted to the base. We already studied the characteristics of this graph, and here I can post them for you again. When we have no frequency, it means that the frequency ratio is equals to 0. The transmissibility factor, or in this case, the displacement transmissibility, is equals to the unit. For zeta equals to 0, which is this green curve. For r equals to 1, the displacement transmissibility goes to infinity. The value for the displacement transmissibility is less than the unity for values r greater than the square root of 2. And for values equals to 2 is equals, the displacement transmissibility is equals to 1. For values less than square root of 2, the displacement transmissibility diminishes with the increase of damping. And finally, we have that the maximum does not occur for 1 when we have greater damping, but occurs at a Rm, which is this expression right here. Now that we have the response of a system which has a moving base with this expression, we will calculate the force transmitted to that moving base of a viscous damp system. Let's draw the free body diagram. We have the force of the spring. Remember that we had relative displacement between the two ends of the spring. We have the force of the damper, and the damper is also with the relative velocity between the two ends of the damper. And the governing equation of this system is the two forces, which are external forces, equals to the inertial forces, which is mass times acceleration. So this transmitted force will be equals to negative mass times acceleration. So let's get the acceleration. For that, we derive this expression twice. And we get that the derivative of cosine is sine, and the second derivative is again cosine, but with the internal derivative, which is omega, we get negative omega squared. If we substitute this second derivative in my force transmitted to the base, we get this expression right here. If we substitute our m times omega squared by k times r squared, because we can multiply and divide by k, so the amplitude of the maximum value of the force transmitted to the base is called force transmissibility, and it has a phase angle. And as you see, this parameter right here, we already discussed it, it's called the transmissibility factor, but now it's multiplied by r squared. And the phase angle between the force transmitted to the base and the displacement of that base will be this angle right here. This is what is called force transmissibility, and is r squared times the transmissibility factor that we already graphed before. But as you see, it changes in the sense that for r equals to 0, the values for this factor are equals to 0. That means if we don't have frequency in our displacement, we don't have force transmitted to the base. For r equals 1, that factor goes to infinity. For r equals square root of 2, all the values are equals to 2 for any amount of damping of the system. The behavior of this r squared times the transmissibility factor changes before and after square root of 2. Before square root of 2, the less amount, the greater the factor. For values greater than square root of 2, the greater the amount of damping, the greater the force transmitted to the base. The maximum occurs after r equals 1. Now let's analyze the response of a damped system under harmonic motion of the base by using a relative coordinate. C will measure the relative motion between the mass and the moving base. C then becomes x minus y, and x will be c plus y. If we add forces in the vertical direction, we have the force of the damper plus the force of the spring will be equals to mass times acceleration. Remember that we don't take into consideration the weight because x is measured from the static equilibrium position and the weight cancels out with the static deflection. If we substitute our relative motion variable, we get c times c dot plus k times c equals to negative mass times c2 dots plus y2 dots. We write our equation of motion as we are used to see our equation. Now let's substitute y2 dots. y2 dots is the second derivative of this displacement. It will be y0 times the frequency square negative sine of omega t. We substitute that in our equation, and this is our equation of motion, and this becomes our non-homogeneous term. If this is the governing equation, the solution then becomes the amplitude of the force divided by the constant of the spring times the amplification factor sine of omega t minus a phase angle. If we substitute the amplification factor and the amplitude of the force, we have this expression right here. K over n, natural frequency of the system, and this becomes R. So at the end, the response is equals to the amplitude of the motion of the base times R squared times the magnification factor. And the phase angle has this form. So we can write that the maximum amplitude can be expressed as R squared times the amplification factor. The relative amplitude variation for a mass damper system under a harmonic motion of the base is then C over the magnitude of the motion of the base, and that's equals to R squared times the magnification factor. This is the graph for R squared magnification factor, which is this expression right here. Characteristics of this graph: R is equals to 0. It means that we don't have any motion of the base. The relative amplitude becomes 0. We have that for R equals 1, which means resonance, and for zeta equals to 0, the amplitude tends to be infinite. Any value of zeta will decrease greatly the amplitude close to the values of resonance. When we increase our frequency of this displacement over here so that R goes to infinity, the relative motion respect to the magnitude of that motion becomes 1. If we derive this expression, it gives you where is the match we will call R critical and is above R equals 1. And this slide summarizes the characteristics of the relative amplitude variation, R squared times magnification factor. Let's move now to the third case, rotating unbalance. We will find the absolute response and the force transmitted to the base due to this type of excitation. Unbalance in rotating machine is very common. Let's see some examples. A laundry machine can get so unbalanced that can even walk. As you see this example in this YouTube video, the machine is almost walking because the vibration is so high that the person decides to turn off the machine. And we can simulate this laundry machine as a mass with an unbalance supported by a spring and a damper. We have other examples as wind turbines or water turbines. They can get very unbalanced and the system can have a large vibration. A simplified model of such machines is shown. The total mass of the machine is m, this right here, and there are two eccentric masses, mass half each, and they rotate in opposite direction with an angular velocity omega. The centrifugal force caused by the normal acceleration of each of these masses will cause an excitation over the mass m. The horizontal component of this force will cancel out and the vertical component of this force will add to 2m half e, which is the eccentric distance, omega squared sine of omega t. If we do our free body diagram, then we will have the horizontal forces will cancel out. We have each of these forces will be half e omega squared sine of omega t, and then we have the force of the spring and the force of the damper. If we add forces in the vertical direction, we have the force of the damper, the force of the spring, minus the excitation force done by the eccentric masses equals to the total mass of the machine times the acceleration of the machine. This can be written as a regular second order differential equation, which is mass times acceleration, constant of the damper times the velocity, constant of the spring times the displacement equals to a non-homogeneous term, which will be our force of excitation. The steady state solution, as usual, is the amplitude of the force divided by the constant of the spring times the magnification factor times the sine of omega t minus a phase angle. If we multiply and divide it by the total mass of the system, mass over k will be the inverse of our natural frequency, and the omega squared times the natural frequency squared becomes r. So then we have that the amplitude will be equals to the eccentric masses times the offset of that mass divided by the total mass of the machine, r squared times the magnification factor. So we can write the response of a unbalanced machine in terms of the unbalance, which is the mass times the offset of the unbalanced mass, times the rotating frequency squared divided by the constant of the springs times the magnification factor, or we can write that amplitude as the unbalance divided by the total mass times the frequency ratio magnification factor. Here we have the phase angle. This phase angle will be between the response of the machine and the excitation force, and in this case the excitation force is the unbalance. Here we have the graph of the frequency ratio squared times the magnification factor. Let's look at some characteristics of this graph. All curves begin at zero amplitude. What does that mean? It means that if the frequency of rotation of the rotating machine is zero, then we don't have any excitation, and therefore the response is also equals to zero. The response near to the resonance is this one right here, is markedly affected by damping. We see that the green curve has a huge amplitude, but when we increase damping, the amplitude diminishes considerably. At resonance, R equals 1. If we put R over here 1, these terms cancel out, and it will be 2 zeta times 1 square, and that cancels out with the square root. then we have that the value for r squared m is equals to 1 over 2 zeta. At very high speeds of the machine, all values, it does independently of the damping, go to 1. The maximum value for r squared, the magnification factor, is not exactly at resonance, but a little bit beyond, right? And it will be at r critical, which is a function of zeta, so it will shift it depending on the amount of damping, and it will take this value. This value is only valid when zeta is greater than 0 or less than 1 over square root of 2. And because for values greater than 1 over square root of 2, which for example is zeta 0.7, as you see the factor r squared over times m does not attain any maximum. And please note that we already analyzed this graph when we study relative motion for a moving base. Now let's study the force transmitted to the base by an unbalanced viscous damp system. If we have this rotating machine that has an unbalance, we already found that the response of the system is this one right here. If we do the free body diagram of the system, we have the force of the spring, the force of the damper, and that is the force, total force received by the foundation or base. That will create a moving force that can affect any other system. And it could be another rotating machine, or it could just be a system that has flexibility and elements that can accumulate kinetic energy, therefore are vibrating systems. And they will also have a response. If this frequency happens to be similar to the natural frequency of this system, the response will be very large. Now, if we want to calculate the transmitted force of this damped system under rotating unbalance, we will do the free body diagram of our base. We will receive the forces of the springs, the forces of the damper, so the force transmitted to the base will be c times the velocity plus k times x. And remember that we already found how much is x, which is the response of the system. Then the transmitted force will be equals to the damper coefficient times the derivative of my response plus the constant of the springs times my response. We can simplify this expression taking into consideration that these terms are the same for both terms, and writing the summation of two sinusoidal forms in terms of only one sine minus a phase angle. This expression here in the square root can be written in terms of zeta and r if we take k out of our square root. Right here is the k, and then we have that k over m is the natural frequency of the system square times r squared. This here is the magnification factor, and we already analyzed that term and we call it the transmissibility factor. Force transmitted to the base done by an unrated balance will be r squared times the transmissibility factor, and the combination of those two phase angles give us this phase angle. And this graph right here represents the force transmissibility, which is r squared transmissibility factor. We have that for r equals 0, force transmissibility becomes 0. For r equals 1, we have the most critical values for zeta equals 0, and damping becomes very significant when we are close to the natural frequency of the system. And after r equals square root of 2, this behavior of the curve inverts. It means that for values less than square root of 2, the greater the damping, the less the transmitted force, but after square root of 2, the force transmitted to the base is much greater when we have greater damping coefficient. In this slide, we summarize the 3 cases we have studied. The first one was when we apply a simple harmonic force, F0 cosine of omega t, we got this response that the amplitude follow the behavior of the amplification factor, and the force transmitted to the base will follow the behavior of the transmissibility factor, which is this graph by here. Then we had the harmonic motion of a base. The non-homogeneous force became this one right here. We analyzed the absolute response. The magnitude of the response will be a function of the transmissibility factor, and the relative response will be a function of R squared, the amplification factor. The force transmitted to the base will be governed by this equation right here, which will be R squared transmissibility factor. And the last case we studied was a rotating unbalance, where the non-homogeneous term in our equation of motion was this one right here. This was our response, and as you see, the amplitude of the response will be a function of R squared times the amplification factor, and the force transmitted to the base will be R squared, the transmissibility factor. At the end, we have 4 important graphs, and those are the expressions for those graphs.